Hi, this is Luke Kane. Today I'd like to talk to you about the U.S. federal debt and how we got there. I got interested in this subject in a debate that I had by email with an old high school friend of mine. In the course of our exchange, he said something I found remarkable. He claimed that President Obama had the worst record with respect to the accumulation of federal debt than any president in recent memory. I thought that was an extraordinary claim, but I had no idea whether he was right or wrong. So before I replied, I thought maybe I ought to check this out. And how did I check it out? Well, I went to my old favorite web page, Google, usually a search engine, to come up with some raw data. I took the raw data, applied some simple mathematics to a Microsoft Excel spreadsheet, and I came to some conclusions, which I'll share with you in just a bit. All right, so I started with the question, how much did the federal debt grow under each president? I chose World War II as a starting point because, well, I was born just after World War II, so these are presidents with which I am most familiar. Now that I've limited the scope, the question is, who were those presidents? And when did their terms begin and end? An interesting side question is, what was the party of each president in question? In other words, did it matter historically whether a president was a Democrat or a Republican with respect to the growth of federal debt? Interesting question. I didn't know the answer at the time. And of course, once I get this data, I'm going to have to find out what the beginning and ending balance of the federal debt was for each of these presidents and somehow measure its growth. But before I do that, I realized I have to modify the data. And there's two modifications I want to make. So I'm going to actually end up with two different data sets. The first data set is going to account for inflation. And why do I need to account for inflation? Well, there are two reasons. The first is that the federal debt is nothing more than a portfolio of bonds. Basically, it's a collection of bonds that the Treasury sells to investors all the time. And the value of a bond is a function of inflation. In fact, the value of a bond is inversely proportional to the inflation rate. But the more important reason is the simple fact from finance that a dollar today is worth more than a dollar tomorrow. This is true because in the period after World War II, there were only a couple of years when the inflation rate was negative. Every other year, though, it was positive, and therefore a past dollar would have more purchasing power than a present dollar. So we need to account for that so that when we compare presidents' balances, we're comparing apples to apples or oranges to oranges. And the other thing that's interesting, the other set of data that we'll collect and modify is something that's going to account for the government's ability to pay off this debt. And the idea is we're going to calculate a ratio of the federal debt to the gross domestic product, the GDP. The idea is fairly simple. If you think of a bank, accepting an application for a mortgage, they're going to create a similar ratio. They're going to create a ratio of the mortgage over your gross income. And if that ratio exceeds some number, like 2 or 2.5, that means that there's a good chance you're a default risk, and you're likely to reject your application for a mortgage. It turns out this is a controversial subject in economics, especially since this paper that was published in 2010 by two Harvard economists. And they argued that once the ratio of federal debt to GDP exceeds 90%, it starts to put the brakes on the growth of GDP. This is a controversial result. Some other researchers at the University of Massachusetts found an error in the original spreadsheet. Those have been rectified. It's still a controversial subject, however. So how do we calculate growth? Well, the easiest way is to calculate the percent growth, which means we just take the difference between the ending balance and the beginning balance of a president's term, and we divide it by the president's beginning balance. This is something right out of middle school. But the problem is this is unfair because it's going to treat Gerald Ford, for example, unfairly with respect to Bill Clinton, because Gerald Ford only served 2 years He only had 2 years to rack up debt. Bill Clinton, on the other hand, had 4 times as many years to accumulate debt. So comparing presidents of different terms using this measure is not fair. It's biased against presidents with long terms. Well, how about an average? Well, yeah, we could collect an average. An average is simply the change in the balance, which we got before. That's the difference between the ending balance and the beginning balance, divided by the change in time. Well, that's just the number of years that the president served in office. Interesting thing about average, though, is if we plot the beginning and ending points of the federal debt on a president's term on a graph, we can connect that with a line. Once we connect that with a line, we can construct a right triangle. With that right triangle, we can calculate a slope. Now, as you may or may not recall from geometry, the slope is defined as the rise over the run. And the rise in our case is simply the change in the balance during the course of the president's term. The run is the change in time. And that, of course, is going to give us the slope. Now, you'll notice that the average is equal to some number, and the slope is equal to the same number. We know from Euclid that when two numbers are equal to the same number, they must be equal to each other. So therefore, slope is equal to average. This will become useful later. However, average has some problems. Average tends to assume an additive process. If you think of your grade point index, basically that's an additive process. You add up the number of grades. If you have 5 grades, you add them up, assuming they have the same weight, and divide by 5. That's what I mean by an additive process. However, averages are weighted against more recent presidents because it turns out that the growth of the book value of federal debt is what's called a monotonically increasing function. Well, I apologize for the math speak. That just means that at every instant of time, the balance is going up. It almost never goes down. And consequently, that means that the averages are going to be larger for more recent presidents than presidents of an earlier time period. Additive processes tend to be linear, and the growth of bond portfolios can be linear, cannot be linear. I mean, it depends. Now, what do I mean by nonlinear? Well, here's an example of nonlinear growth. I mean, basically, the growth is of a number of microbes in a petri dish is represented by this curved line. And if we want to measure the growth rate at some time t, we extend a line from the x-axis up to the curve, and we put a point there. So we're interested in finding the growth rate at this particular time t. To do that, we're going to draw a tangent through the point. Now, here the tangent is represented by a green line. Once we have the tangent, we can construct a right triangle, just as we did before. And once we construct the right triangle, we can calculate the slope. And the slope is going to equal the change in the number of microbes over the change in time. Now, this slope that we're calculating at an instant of time in mathematics is called a derivative. It comes to us from calculus. In economics, it's called a marginal growth rate. So how do we calculate bonds? Well, bonds grow by multiplicative process. And to understand what I mean by multiplicative process, let's do this by example. Suppose you buy a $100 bond that will pay you $150 in 3 years. That begs the question, how much did it grow each year? To do that, we're going to need to calculate a geometric average. And once we calculate a geometric average, we'll be able to calculate the more interesting number, which is a compound annual growth rate. So let's do that. All right, to solve this, we start by putting $100 in the bank. That's our beginning balance, also known as our principal. Now, at the end of the year, they're going to take this $100 and they're going to multiply it times the compound annual growth rate. And that's going to be the balance at the end of our first year. Now, we can factor out a common term, in this case 100, and when we divide the first term by our common factor, 100, we're left with 1. Do it to the second term, and we're left with r. This is an equivalent form of the balance at the end of our first year. Okay, so now we move on to year 2. The beginning balance for year 2 is the same as the ending balance for year 1, which is 100 times 1 plus r. Plus, well, we're going to take the beginning balance, which is 100 times 1 plus r, and again, we're going to multiply that times the compound annual growth rate, which is the implicit growth rate in this particular bond. And again, we can factor out common term, which in this case is 100, 1 plus r. And when we do that, well, divide the first term by the common term, and we get 1. Divide the second term by the common term, and we're left with r. You may be seeing a pattern. This is the balance at the end of the second year. Well, it's also the balance at the beginning of the third year. And we do this all over again. 1 plus r, plus we're going to multiply our compound annual growth rate by the initial balance, the balance at the beginning of the year, and that's 100 times 1 plus r times 1 plus r. And again, we have a common factor, which we can pull out, and when we pull it out, it's 100, 1 plus r times 1 plus r. And then when we factor in the common factor, we're left with 1 plus r. You can see the pattern grows. If I were to calculate the balance at the end of 4 years, I would multiply this whole thing by a factor of 1 plus r. The balance at the end of 5 years, I'd multiply that whole thing by 1 plus r. This is the geometric mean. Okay? It is the amount, is the factor by which I grow my balance from year to year. Well, I'm only interested in 3 years, because at the end of 3 years, my balance equals $150. So now I have one equation with one unknown, which means if it is solvable, I can solve it. And I'm pretty sure we can solve it. Now, first thing we're going to do is simplify it. 1 plus r times 1 plus r times 1 plus r is the same as 1 plus r quantity cubed. And that's going to equal $150. All right, we're going to get rid of this 100 by dividing both sides by 100. We have to divide both sides to keep the equation equal. Okay, 100 divided by 100 is 1. 1 times anything is anything, so we're left with 1 plus r quantity cubed, my ending balance over my beginning balance. Now I can simplify this. This is going to be 1.5, or 3 halves if you like. 1.5 is easier for the calculator. All right, now I want to get rid of this 3. How do I do that? Well, I take a cube root. And again, I do it to the left-hand side. I must do it to the right-hand side. The cube root of a cube is whatever is inside the parentheses, which is just 1 plus r, which is the cube root of 1.5. Now, we're going to generalize this formula later. 1 plus r is the geometric mean, and it's equal to the nth root, where n is the number of years, of the ending balance over the beginning balance. But what we're really interested in is the compound annual growth rate. And to get that, we're going to subtract 1 from both sides. When we do that, well, this is 0, so that doesn't add anything. So we're left with r. r equals the cube root of 1.5 minus 1. Now, again, we're going to generalize this formula. For n periods, the compound annual growth rate would be the nth root of the ending balance over the beginning balance minus 1. So let's see if we can calculate this beast. Now I look over here for a cube root function. Here's a square root function, but I can't find a cube root function. Well, that's okay. I can modify this equation slightly. I'm not going to change it. I'm just going to change it to an equivalent form. The cube root of 1.5 is the same as 1.5 to the 1/3 power. And I subtract 1. This I can calculate. So let's calculate it. I have 1.5 raised to the 1/3 divided by 1 divided by 3. And I'm going to move out of the exponent. Minus 1. Enter. And I get this number. So R is equal to, according to this, 0.1447142426. Well, let's just round that off a little bit. R is approximately equal to 0.1447. That should be close enough. And that, of course, is equal to 14.47%. All right, let's check that. I always like to check my answer to make sure it's reasonable. How do I check it? Well, let's go back to the original equation, which is buried in here. Well, let's recopy it. The original equation is 100 times 1 plus R cubed equals $150. Well, I've got a solution for R. Let's plug it in and see if it works. All right, so I have 100 times 1 plus 0.1447. This whole thing is going to be cubed. And this whole thing should equal $150. But we don't know yet if that's true or not. Let's check it out. All right, so we're going to multiply 100 times quantity 1 plus 0.1447 quantity. Now we're going to cube this whole thing, and we should get $150. Oh my goodness, we don't. We get $149.99 and some change that's less than a penny. So apparently this is slightly off. This is equal to approximately $149.99. Why are we off? Well, it turns out this cube root function, right, of 1.5, this is an irrational number, which means that its decimal expansion goes on forever. So the digits that we saw are not all the digits in that number. So let's expand our calculation, put in some more digits, and see if we can get closer. All right, so this time we're going to do 100 times, all right, I'm going to do the addition in my head, not hard to do, 1.1447. And let's double our precision, hopefully, by doubling the number of digits that we go. So we're going to go 1424. 1424. Close parentheses. Actually, I don't need the parentheses. Sorry. And now this thing I'm going to cube. And if I don't get $150, I should get a little bit closer. And I do. But it's $149.99999. Point is that the bank here would round this off and you would get your $150. And that, ladies and gentlemen, boys and girls, is how we calculate a compound annual growth rate. Okay, so we calculated the geometric mean. We generalized it to this formula where the geometric mean, which is 1 plus R, remember that's the factor by which we grew our initial balance. Each year we multiplied times this factor, and that gave us a new balance for the next year, and so on. Anyway, we do this for n periods, n years. So in the case of Gerald Ford, that n would be 2. He served for 2 years. For Bill Clinton, that would be 8. And then we take the ending balance divided by the beginning balance and put it in this radical sign. Now, what we're really interested in, however, is the compound annual growth rate. And for that, we just subtract 1 from our formula for the geometric average. And in our case, we got approximately 14.47%. Recognize that if we want to be more precise, we would go out as many digits as you like. In other words, we can be as precise as you want. Now, let's collect some data. And thank you, World Wide Web, and thank you, Google. How did we ever survive doing stuff like this before? Bunches. So to start our data collection, we go to Google. And using this search engine, it's very easy to find a list of presidents on the Wikipedia webpage. This suits our needs perfectly because it gives the name of the president, the date that they took office and the date that they left office. It also gives the political affiliation for all 44 presidents, starting with President George Washington and ending with President Barack Obama. So with this, we're able to calculate a spreadsheet. And then you'll notice we have 12 presidents after World War II, starting with Harry Truman, whose administration began in 1945. Actually, it began in 1944, but he had no control of that particular budget. His budget didn't actually start until 1945. In any case, we go all the way up to 2013, which is last year. This recording is made in the summer of 2014. Now all we need to do is find the beginning balance of the federal debt and the ending balance and adjust it for inflation. Once we do that, we can calculate the percent increase. But as you know, the percent increase is going to be biased against presidents with longer terms. We can calculate the average growth per year equally easily. However, that's also biased. That's going to be biased against more recent presidents. And the only measure that we have that isn't biased in either respect is the compound annual growth rate. But to calculate that, we're going to need to know how many years was each president in office. Well, that's an easy calculation to do with the data we've already got. Harry Truman's presidency ended in 1952. So we want to subtract 1944. Well, we don't have 1944, but I can take 1945 and subtract 1. That's going to give me 1944. When I enter that, bingo, I get the 8 years that I expect. I copy that formula and I get the length of the terms of all 12 presidents, and let's see, what's the sum? The sum is 69 years. So we're going to look at 69 years in the growth of the federal debt. And the question is, where do we find these numbers? And the answer, of course, is we go back to Google. All right, when we go to Google, very quickly, we get this page. On the White House website, there's a page for the Office of Management and Budget. Lists a whole bunch of tables, but it lists a table that's exactly what we're looking for. The federal debt at the end of the year from 1940 to the year 2019. Obviously, those are some estimates because it's only 2014. So I click on that, and my browser asks, do you want to open that with Microsoft Excel? Yes, I do. And I get this. Excellent. Now I want to enable that. All right, let's look at what we've got. We've got the end of the fiscal year for 1940. What are the units of measure? They're millions of dollars. So this is millions, billions. The end of fiscal 1940. The book value of the gross federal debt was a little bit more than $50 billion. And then we go up to 1982, and it had grown to $1.1 trillion. Excellent. I don't care who held the debt, so I'm going to hide those data. I'm going to hide that data. Oh, look at this. Gross federal debt as a percentage of GDP. Oh, that's excellent. That's just what I wanted to look for. Now, I actually checked these numbers out. I looked for historical GDPs at other sites, and I looked at also looked at the federal gross debt on the Treasury page, and double-checked these numbers. And I now have two sources that check them out. If you want to check them out, be my guest. The sources are referenced at the end of this video. And as before, I don't care who held the debt. So I'm going to hide that data. All right, so now what I need to know is I need to know the inflation rate. Well, guess what? I'm going to go back to Google. And when I go back to Google, I'm going to find this page on the Bureau of Labor Statistics. And basically, it gives me historical inflation rates by month and year going back to 1914. So I'm just going to copy this whole thing. All right, I don't want to do 2014. I don't need that. That's extraneous. So I copy that, and I go to my web page, and inflation. And let's see, I put it right here. Paste. Okay, I don't care about monthly inflation rates, so I'm going to hide that data. May use it sometime else. And you'll notice it gives it as 1%. Well, I don't want percent. I want it as a decimal. So I'm going to divide by 100. So that's pretty good. Now, to do the adjustment for inflation, I'm going to end up multiplying times the factor of 1 plus the inflation rate. So I need to add 1 to all of these numbers. 1 plus that is that. All right, and I'm going to copy that for all of my data. Boom, 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 boom. Yow. And it goes all the way up to 2013, which is a good thing. And let's just take a quick look at this data. You'll notice that every year it goes up. Inflation goes up, which justifies our axiom that, oh, wait a minute, it didn't go up in 1955. It went down. Don't know what happened in 1955. Let's look a little more closely. Any other negative numbers? Oh, yes. Look at 2009. Flight prices actually went down 0.4%. Well, except for those 2 years, we can now, a couple more years in the 20s. Oh, yeah, pretty nasty in the 20s. But we don't care about the 20s. Anyway, we can still say that a dollar today is worth more than a dollar tomorrow, and this data tends to bear it out. But that's a tangent. Let's go back to what we need to do. Now we need to change these dollars into 2013 dollars. And the easiest way is to work our way backwards. All right, so 2013 dollars, well, that's going to be easy. That 2013 is already in 2013 dollars. Now, where do we have to go next? All right, so now we got to go back to 2009. Well, the beginning balance of 2009 is actually the ending balance. Remember that our data is in ending balances, so we have to go down to 2008. All right, we can do that. So 2008. 2008. So 2008, the book value was that. All right. Now I'm going to multiply that. Oops, multiply times the product. Okay. Of times the product of the inflation rate from 2009 to 2013. 2009. Where is it? 2009 to 2013. Close parentheses. And voila, here's what I get. Okay, so in 2008, 9.986 trillion was worth 10.807 trillion in 2013 dollars. Once I was able to do that, I could very quickly fill in the table, and this is what I got. All right, and I did the similar type of thing for the federal debt as a percentage of GDP, and I got this data. Let's look at this a little more closely. Okay, now we're going to look at the results a little more carefully. And turns out my friend was right, and in one sense he was actually wrong. So let's look at the results. And the most interesting result is the debt as a percentage of GDP. Now the idea is the higher this ratio is, the less affordable the debt is. And if you believe the controversy in economics, eventually it starts to put skids on the growth of the economy. So if we look at the debt as a percentage of GDP since World War II, interesting feature. It goes down. Well, a little blip in the Truman administration, but it goes down in the Eisenhower administration, the Kennedy administration, the Johnson, Nixon, Ford, and Carter. Well, looks like it went up a tad in Ford, but not much. So the trend is definitely down. But then a funny thing happened. President Carter lost the election to President Reagan. And guess what? The debt as a percentage of GDP grew under President Reagan in almost a straight line. And it continued to grow under the administration of his Vice President, George H.W. Bush. And you'd expect it to keep going up, but oh no. Under President Clinton, it actually went down. But then President George W. Bush, well, not too bad. But then at the end, the economy hit the tank, and the ratio goes up until it gets to President Obama. So that's basically, we have a big U shape. You'll notice we started at just under 100%, and we're ending at just a little tad over 100%. So we went through this big cycle to get back to where we started. All right, so who the winners, who the losers in terms of CAGR? Well, my friend was right. President Barack Obama is the highest with a CAGR of 9.12%. That's higher than anybody else. Number 2 is Ronald Reagan. This was a surprise. I didn't expect that. He was just a tad less growth rate than Barack Obama. And next is an even greater surprise. The next 3 are all Republicans. George H.W. Bush, George Gerald Ford, and George W. Bush all had significant CAGRs. We look at the next group, and they're all Democrats. And then we have a mixture of Democrats and Republicans. You'll notice it gets negative down here. I'm not going to try and explain that. I suspect it has something to do with the fact that all 3 of these suffered recessions. All 3 of these had inflation, as I recall. It was in double digits. But I'll let the economists figure out what that means. I'm just here keeping score. All right, well, that's the federal debt adjusted for inflation. How about the CAGRs for the debt to GDP ratio? Well, again, President Obama comes in first with 8.24%. Ronald Reagan's behind by him by 5.66. And guess what? It's all Republicans. It's the same cast of characters. And followed by a bunch of Democrats. And last, Nixon and Johnson bring out the end of the list. And you'll notice that most of these presidents had negative returns. That means their economy was growing faster than the debt was. Now, if we look at how the political parties did, this was the big surprise for me. The Republicans in the 69 years that we looked at had an average, a compound annual growth rate of 3.82%, while Democrats had almost half of that at 1.45%. If you look at the 69 years of growth in the federal debt in terms of 2013 dollars, the average comes out to 2.68%. It gets a little strange when you look at the ratio, but it bears out what we already knew. The Republicans had a positive CAGR of 1.13%, which tells us that if a Republican's in the White House, chances are that the debt's going to go up in terms of real dollars. Remember, these were measured in 2013 dollars. But if a Democrat's in the White House, the ratio is going to become negative, and the ratio of debt to GDP is going to go down. Now, let's look a little closer at President Obama. That's beginning to look like a curve to me. Okay, so let's plot the U.S. federal debt to GDP ratio for the Obama administration. We're going to start in 2008. The ending balance of fiscal 2008 for this ratio was 67.7%. That's going to be President Obama's beginning balance. And his ending balance is going to be the ending balance at 2013. All right, so we're going to insert a scatter plot. It's going to look like that. And here's our scatter plot. Okay, we don't need this. And we can squish it together to give it more of a curve look. And we can emphasize the curve look by adjusting the x-axis. We're going to fix the minimum of the y-axis to be 60%. Okay, and we get a curve that looks, oops, and one more thing. We want to make this 0. So what we're going to do is move that over a little by selecting the series. We're going to edit. We're going to put in a range for our x values. We're going to start with 0. That's the ending balance for fiscal 2008, which, as I said earlier, is the beginning balance for 2009. And we're going to go up to the ending balance for the 5th year of President Obama's term, the last year for which we have data, which is the end of fiscal 2013. So we put that in there, and oh good, it moves that over to 0, exactly what we wanted, and we're good to go. Now here we go. There's the curve that we wanted. I can squish it a little more, I suppose. There we go. All right, now I want to fit the curve. How do I do that? Well, I add a trend line. Now the trend line that Microsoft always starts with is a linear trend line. That is a line. Well, you can see that these data points don't actually fit the line very well. Only one point actually hits the line. 3 of the points are above the line. 2 of the points are below the line. Not a good fit. Let's see if we can get a better fit. We're going to make it a polynomial. Polynomial of degree 2. That means we're going to have a function that's some constant times x squared plus some constant times y squared plus some constant. Wow, we get a better looking fit. Looks like everything's getting closer. Now let's make it even closer by having a polynomial of degree 3. Oh, excellent, excellent, excellent. That's a really nice fit. And let's just see how good a fit it is. We're going to display the equation because we're going to do a calculation on that later. And we want to display the r squared statistic because that's going to tell us how close the fit is. And when we do this, here is our polynomial of degree 3. Polynomial of degree 3, our cubic equation, that simply means that the highest exponent of x here is 3. Now r squared, this is very good. R squared here is 0.9992. That means that this is a very, very good fit, about as good a fit as you're going to get in the real world. If this were a perfect fit, all right, you can see that these 2 points here don't exactly pop on the line, but if every point was exactly on the line, r squared would equal 0. R squared would equal 1. If, on the other hand, these data points were completely random, such that no curve could fit, then r squared would be at its other extreme, which is 0. Now, since r squared runs a range from 0 to 1, we see that r squared equal to 0.9992 is a very, very good fit. That's a good thing. Now, I want to plot one more curve. Okay, and to do that, what I need to do is calculate the CAGR for President Obama. We've already done this. You've seen it in the table, but let's just do it again as a double check. So we take the ending balance and we divide it by the beginning balance. And we take the 5th root, which is the same as raising it to the 1/5 power. The reason we're doing the 1/5 power is because we have 5 years in question. Okay, and then of course we're going to subtract 1, so we get our CAGR. Otherwise, we're going to get our geometric mean. There's our CAGR. It's 8.24%. Actually, as you know, this is an irrational number. It's 8.24 blah, 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 going on to infinity. Now, what I want to do is I want to start with my beginning balance, and I want to grow that beginning balance by this growth rate. Now, how do I do that? Well, I take the beginning balance, and I multiply that times the geometric mean, which is 1 plus CAGR. And I put in an absolute address, so I can copy this later, and voila. At the end of the first year, if I start at 67.7% and I grow the balance by 8.24%, I end up at the end of the year with 73.28086. I'm sure that goes on for a long time. But anyway, now I'm going to do that over and over again. I'm going to do that up until I get to 2013. And if I did this correctly, I should end up with an ending balance of 100.6%. And I did. All right, I want to plot that. All right, so what am I going to do? Well, I'm going to go back to here. Here's my curve. and I'm going to amend it. I'm going to add another curve. So I select data. I'm going to add a data set. My y values are going to be these guys. Okay, and my x values are going to be the same x values as before. And you'll notice I get a straight line. And let me draw the straight line just so you'll see it. All right, let's fit these data to a trend line. Again, it's going to go, Excel is going to pick a linear trend line. And let's display the equation and display the r squared. This is interesting. It too is a very good fit. It should be a perfect fit. I think what's happened is we've seen the accumulation of round-off error, a common problem amongst computer applications that have to deal with irrational numbers. Because this r squared should be 1. It's not, and that's a problem with this computer application and the computer. But anyway, it's close enough. And you see it's linear because x is raised to the first power. This CAGR, all right, this line, as you recall, this is going to be the average for President Obama's administration, all right, a number that we calculated earlier. We're going to look at this average in a more dynamic view of this graph in just a moment. All right, so here we've plotted President Obama's debt to GDP ratio in each of the at the end of each of the first 5 years of his term. So this is the balance that he began with, and this is the balance that he ended with in 2013. We saw earlier how we could fit that to a curve, which we did here. And now that we've got it on a curve, we can now put a tangent on that curve. Now remember, the tangent is going to tell us the growth rate at this particular instant of time. So this particular instant of time is somewhere between the second and third year of President Obama's administration. And at this point, his growth rate is growing at 5% per year. Well, how do we know that? Well, that's because we measured the slope at that particular point. And of course, we saw this earlier. It's rise over the run. If we animate this, you'll see that the rise stays constant while the run gets larger, and it continues to get larger and larger, so that since the denominator is getting larger and larger, the slope is getting smaller and smaller. Okay? So let's it's a lot of clutter with that triangle, so let's put that triangle away. What we're interested in is in this. So let's look at where President Obama began. All right. In 2008, the beginning balance of the federal debt, it was growing at a rate of almost 17.5%. That's staggering. That's huge. Okay. And then by the end of 2013, he reduced that continuously to about 1.44%. That's a 90% reduction. I want to repeat that. That's a 90% reduction. That's extraordinary. Now, let's look at the secant. This secant is what we calculated with the CAGR. If you remember, we did this earlier. We ended up with a straight line when we plotted the growth rate in terms of its geometric mean every year. This is when in a straight line from A to B, and this gives us an average of 6.58, which is the highest that we can get. And if we go to the sort of midpoint in his in this thing, it's actually after only 2 years. President Obama's, this is his marginal growth rate. The marginal growth rate has equaled this average growth rate, and then it just continues to get better. Okay, this is extraordinary. He's changed the debt to GDP ratio by more than 90% in the course of 5 years. of his administration. And if we look at how that would change his rating in terms of average. So let's do that. All right, so here is President Obama's 6.58, which, as you can see, by this measure, he has the highest average growth rate. Now remember, average growth rate is biased against more recent presidents. But let's put it at his ending marginal growth rate, which was 1.44. And let's see what happens to his rating then. So we're going to sort the data, and we're going to sort it by, let's see, column J, and we're going to show the largest to the smallest, and look what happens. President Obama goes from being number 1 to being number 4. All right, so if you look at how he has reduced the average growth per year of the federal debt to GDP ratio, he goes from being first to fourth, which I think is extraordinary. And of course, he is preceded by the same usual suspects, George Bush, well, the two Bushes, and President Reagan. I think that's an extraordinary accomplishment that somehow has been overlooked in the debate over the federal debt in President Obama's administration. Okay, let's sum up. But before we get to the conclusions, let's take a little closer look at marginal growth rates. The marginal growth rates that was shown earlier in the dynamic model was really an approximation based on a geometrist sketchpad model. And the visual model was used so we wouldn't have to explain marginal growth rates using calculus. The visual model showed that from 2008 to 2013, President Obama's marginal growth rate for the debt over GDP ratio declined by slightly more than 90%. The actual marginal growth rates for the fitted curve are a little bit better, and we can see this by using a little bit of calculus. This is the curve that we fitted to President Obama's debt to GDP ratio over the first 5 years of his term. When we take the derivative, we get this function. When we evaluate that derivative at 0, in other words, at the beginning of President Obama's term, we get a debt to GDP ratio growth rate of 17.623%, which is rather stunning. This is also the marginal growth rate of the debt to GDP ratio at the end of President Bush's administration. Now, when we take the derivative and evaluate it at the end of the 5th year, which is at the end of 2013, the marginal growth rate for the growth of the debt to GDP ratio has fallen to 1.446%. So when we actually use calculus to calculate the marginal growth rate for debt over GDP, we see that it's actually improved by a little more than 91%. And our model was showing that it was a little over 90%. Basically, it's the same order of magnitude. It's the same solution. So now I think we can wrap up. All right, let's sum up. The federal debt to GDP ratio during President Obama's term could easily be fit into a curve. And that curve, it turns out, is very, very good. It has an R squared of 0.992. 3 nines and a 2. So this is a very, very good fit. We saw that if we plot the growth in terms of CAGR, it grows as a linear path. And we saw that if you put in the marginal growth rate, which was the growth rate at this point, basically President Obama ended up in 4th place in terms of the growth of the federal debt to GDP, with 3 Republicans, the 2 Bush presidents, H.W. and W., and Ronald Reagan in the middle. So President Obama, although his numbers look bad, they have improved extremely well in the course of his administration. So, since World War II, yes, it's true, my friend was right. Obama had the highest growth rate in federal debt. However, his marginal growth rate has declined So he falls from first place to fourth place when compared to the 12 presidents' average growth rates. And to me, the biggest surprise of looking at this data was how poorly Republican presidents did with respect to the growth of federal debt. Basically, during a Republican administration, on average, the federal debt grew by twice the value that it did during a Democratic administration. This has been an interesting study. I thank you for waiting all the way to the end here. I'm Luke Kane. Thanks for watching. Bye now.